All right, it is 10, so we will get started for today. Just a little bit of review of what we talked about on Monday. We looked at the subatomic particles in atoms, talked about isotopes, which is same number of protons, different number of neutrons. And we talked about ions. One sec, sorry. All right, and we talked about ions, which are same number of protons, but different number of electrons, and where you have a cation, which is positive, so more protons than electrons. And you have an anion, which is more electrons than protons. And the last thing we're going to talk about for this PowerPoint is just the different types of groups we have in our periodic table. So again, I'll repeat, it's very helpful to have a periodic table up for the rest of the semester, at least have one nearby. I would suggest to print one out and look at it like that, especially when it comes to test time. You don't want to be on your phone. It looks super suspicious. So make sure you just have like a periodic table with you. And there is one up on Blackboard if you'd like to print that out. So let's take a look at the periodic table in the top left here. And we have three basic categories of elements. We have metals, which, let me get my lines right. Here are everything that's a metal. We have nonmetals, which are right here, and those are nonmetals. And then the purple that is left, those are called metalloids. Metals, generally, what they do is that they conduct heat very well. They conduct electricity very well, and they're malleable. That is, you can mold their shape. Nonmetals are the opposite. Nonmetals don't conduct electricity. They don't conduct heat, and you can't really form their shape. Like, imagine that you're trying to shape oxygen into a cube. Good luck, right? It's gas. Metalloids are the in-between of metals and nonmetals. They're okay at conducting electricity. They're okay at conducting heat, and they're somewhat malleable. The way to keep this in mind on the periodic table, if I get rid of my drawings, is that on most periodic tables, you're going to find this really dark ladder looking thing. And generally, whatever touches that ladder is a metalloid, with aluminum and PO being an exception there. Anything to the right is a nonmetal. Anything to the left is a metal, with the exception of hydrogen. Now, when we look at groups, and when we're talking about groups, we're talking about columns. So a column is a group. 1As are what we call the alkali metals. These metals are incredibly reactive. It's very rare to find these metals in their pure forms on Earth. They're usually in a compound already. And in fact, if you do have a pure form of this metal, it will react very fast. So sodium, you've probably never seen pure sodium before, but it's like a really pale silver. And what happens is that this silver will like dull very fast because it reacts with the air. So if you cut pure sodium, it's like cutting butter, but it's a metal. So it's really, really odd. When you cut it, the inside is going to be super shiny because it's pure sodium. Within a few seconds, though, this shininess will become dull because it reacts with the air that it's now exposed to form compounds. And if you throw these pure metals into the water, you create like explosion. So if you take a brick of pure sodium, throw it into a lake, it's a giant explosion. because that sodium reacts so fast with the water and release so much heat in such a short amount of time. It's like a bomb going off almost. So if you're ever bored on YouTube, look up, solid sodium or solid lithium in water. You'll find videos of people doing this. So the alkali metals themselves, what do they do in a chemistry context? Well, metals in general, what metals like to do are form cations. Metals like to get rid of electrons. And the group 1 metals always form a +1 ion. So they always form a +1 ion when they react in a reaction. While group 2 metals, the alkaline earth metals, they're reactive, but they're not as reactive as the group 1 metals. So if you were to throw solid calcium, which you can buy in the store, right? You can buy calcium pills. If you throw that into the water, you're going to get some fizzy, but you're not going to get an explosion. And these are somewhat stable in the air. Solid magnesium you can buy as well. They'll corrode, but it'll be much slower. These form +2 ions. Outside of group 1 and group 2, and some exceptions like aluminum, we don't know what ion will form. These are called transition metals. So everything in the middle of the periodic table, they can form different ions. Each element in the transition metals can form at least 2 different ions in a reaction. And with some exceptions, aluminum, zinc forms +2, and silver forms +1. Everything else, we can't just know by looking at the metal what ion it will form. If we look at our nonmetals, these nonmetals form anions. They want to get electrons. Our group 7, they're called the halogens. These are incredibly reactive gases, very hazardous gases. So pure fluorine will wreak havoc on your lungs. Pure chlorine will kill you as well. And I also didn't mention, but the group 1 metals are also poisonous, like sodium. By the way, who wants to tell me what happens? What do you get when you mix sodium and chloride? What is that element called? Or what is that compound called, rather? Bleach? Nope, it's not bleach. That's ammonia and what else is it? It's like hypochlorite. Salt. There we go. Salt. So sodium, poisonous. If you eat it, it'll kill you. Chlorine, poison. If you break it or you breathe it in, it'll kill you. Combine these together, they make a tasty compound. So this also shows like that when you have ions, ions react differently in chemistry than their neutral counterparts. When I say poison for sodium, that's neutral sodium. When I say poison for chlorine, that's neutral chlorine. You get it in the ion form and you combine them, you get tasty salt. So halogens, very reactive, incredibly reactive, but they're also poisonous. Your group 8, they're called noble gases. So they're also nonmetals, but they do not react at all. So they will never interact like in a chemistry reaction. They're always going to be spectators. They're always going to watch. We're going to talk about later on in the semester why that is. But for now, it is good enough to know if you have something that's a noble gas, which are right here in the big periodic table, they'll never react. Halogens, always -1. Group 6, 6A, oxygen, always -2. And then nitrogen's always -3. And so when we go through chemistry this semester. Always keep that in mind for these ions, the positive and the negative ones. It's going to make your life so much easier once you commit that to memory, that group 1 plus 1, group 2 plus 2, nitrogen minus 3 for the most part, 6A minus 2, 7A minus 1, and noble gases neutral. They don't react. All right. Any questions about any of the material presented here or anything at all? All right. So I do have a little exercise for us to get used to the periodic table. This one is cut off, but it says oxygen. I want you to just get familiar with the tool of the periodic table. So write the name of each element. Tell me what is the charge of each element. Is it metal, non-metal, or metalloid? And then take it one step farther with alkali, metal, alkaline, halogen, or noble gas. So I'll give everybody a few minutes to just look at their periodic table, find these elements, get used to the ions and classification schemes. What do the A and B signify on the periodic table? Let me go back. So the A, so like 7A, 8A, those things are, I believe, are the columns if you ignore the transition metals. Because if you look at the top of the periodic table, and sorry, I'm going to go back one more for those of you working, I apologize. If you look at the top of the periodic table, it goes 1, 2, 3, 4, or it goes 1A, 2A, 3A. So the A's is just like, I'm going to skip the transition metals. The B's, I actually do not know off the top of my head because I have never used the naming scheme of 3B, 4B, 5B. So good question. I actually have never looked that up in my life. I've always just ignored that and just used either 1A, 2A, 3A, or the 1, 2, 3, 4, 5, 6, 7, 8. All right. So if you have questions about this, let me know. Otherwise, I will be back in a few minutes to go over the answers for these. Remember, if you're feeling stuck, want to check an answer with me, always feel free to send me a message. And you can always send me a private message as well. Or if you just want to chat, all done. Tell me how your day is going. That would be great as well. All right, so hopefully you have had some time to at least do a couple of them. I'm going to move on so we can catch up to where we're supposed to be today. A, F. Well, F, that element is fluorine. That is a nonmetal because it's on the right-hand side of the periodic table. It's in column 7A, so that would make it a halogen. And everything in that column will always form a -1 charge. So I'm going to do it a little bit out of order from what I had 1, 2, 3, 4 there, but everything should be there. Next one, special K is potassium, the thing you find in bananas. Calcium, or it's not calcium, potassium. Potassium is a metal. So when you eat bananas, you are eating metal. Well, a very, very, very small amount of metal. Potassium is an alkali metal. It's right there in the first column. And alkali metals have a +1 charge. Ne would be neon. If you ever go to Las Vegas, they are shooting electricity through neon to make it glow. Neon is a noble gas. It's all the way over to the right. It's on the farthest right column of the periodic table. Anything over there is a noble gas. These are all nonmetals and has no charge because it's a noble gas. Mg is magnesium. Do not get confused with Mn. Mn is manganese. Mg is magnesium. Two different things. You'll find this in the second column, which means it's +2. It's on the left-hand side of the periodic table, which makes it a metal. And since it's in the second column, this is an alkaline earth metal. Lastly, we have oxygen. Oxygen's a nonmetal. It's in 6A, so that means it's always -2, but it doesn't have a name. It's not any of those classification schemes, so no group name that we learned. So when using the periodic table, this is some of the information that I want us to know. We should be able to look at a periodic table and know what's a metal, what's a nonmetal. We should know the basic groupings of halogen, alkali metal, earth metal, and noble gas. And we should be able to know just by looking at an element and its position on the periodic table, in a reaction, what charge will it become? That will make our lives so much easier moving on once we have that information. Because as we move on in the semester, I'm just going to kind of assume you know this information. You know what's a metal and a non-metal. You know what charges metals get, what charges non-metals get. And if we know that, we can talk about more complex things, talk about more complex chemistry. But from this, is there any information or any questions about any of the information presented here, or what I expect you to know, or anything like that? What PowerPoint this? This is the PowerPoint for Monday. We will shortly transition over to Wednesday. All right, if there's no questions, we will make that transition now. So let me pull up the Wednesday PowerPoint, today's PowerPoint. And we're going to continue to look at the periodic table. I'm going to rewrite what that says down there. All right, so looking at the periodic table, when you look at elements, you're going to see a couple numbers, right? You're going to see the symbol right here. You're going to see the number. That's number of protons. So chlorine is element number 17. You're going to see a number down here that usually has decimals in it. This is average weight of 1 mole of chlorine in this case. Or it's just the average weight, or it has two definitions, average weight of 1 atom. So for chlorine, this 35.45, it's either atomic mass, which I have a formula up there for, so the weight of 1 atom, or the average weight of 1 mole. Now, how do we actually calculate this number, this weight that's found for chlorine? We use this equation shown here. And since this is really the first equation we've used in this class, I'll just say for our test, you will be given an equation sheet. So I do not expect you to memorize any equations. What I expect you to do, though, is be able to understand the equations and use the equations, because the tests in this class are basically going to be the same as the problems we're doing right now. So if you don't know how to do the problems right now, you're not going to be able to do them on the test. So that's why we do them in class. So make sure when we go over equations like this, you know how to use them, you know what they're saying. So let's see what this equation is saying. It's saying the atomic mass of an element is equal to this giant E. So this is sigma, the uppercase sigma. And what this means, if you don't remember from your math class, is addition. This is saying add up everything that comes after this. This n means number of times. So do this addition n times. So n could be like 3, n could be 4, n could be 1,000,000, any number. And the equation that comes after it is what we're going to be adding together. So to find atomic mass, we're going to take the fraction of isotope of a certain isotope n times the mass of isotope n. Well, what does that actually mean? So let's say chlorine has 3 different isotopes. And remember, an isotope, same number of protons, different number of neutrons, right? So let's say chlorine has 3 isotopes, and I'm going to just make up numbers. I think we actually do a real example here in a second, but I'm just going to make up numbers. So let's say isotope number 1 has 17 protons and 18 neutrons for a weight of 35. Isotope number 2 has 17 protons and 17 neutrons for a weight of 34. And isotope number 3 has 17 proton plus 17 neutron, or 16 neutrons for a weight of 33. Again, I'm just making this up. So that's what the mass is. And the fraction is, if I take a sample of chlorine, just a random sample, what percentage is made out of each isotope? So let's say, I'm going to do the math easy on me. So let's say 60% is made out of isotope 1, 20% of my sample is made out of isotope 2, and 20%, that was a weird zero, 20% is made out of isotope 3. Right. So that's my percentages. To use this in an equation, I take my percentage, divide by 100. So anytime you want to use a percentage in a calculation, you must divide that percentage by 100. So to get the atomic mass of this made up example I just made, I'm going to take 0.60, which is 60 divided by 100, multiplied by the mass, which is 35, plus, that's where this sigma is coming in. It's saying, do this for each isotope and add up your results. Plus, so this is isotope 1, I1, plus isotope 2, I2. The fraction of isotope 2 is 0.2 multiplied by the weight, which is 34, plus isotope 3, and I'm running out of space, so I'm going to erase here. Isotope 3 is also 0.2 times 0.33. So you take your isotopes, fraction times weight, fraction times weight, fraction times weight. You add them all up together to get an overall atomic mass. And that is what is reported on the periodic table when we talk about masses. So it's one thing to watch me do it. It's another thing to actually try and do it. And so, yeah. So based on the example I just gave you, like when I just worked it out. So we have this question. So I want you to try and find this. So silicon has 3 isotopes: silicon 28, silicon 29, and silicon 30. The mass and abundance of silicon 28, the mass is 27.9769 atomic mass units. So AMU, atomic mass unit, is just weight of one atom. That's what atomic mass unit is. And the abundance is 92.2%. Silicon 29, weight's given, abundance is given. What I want you to do for me is use this equation, the atomic mass equation. Tell me the mass and abundance of silicon 30 if the actual atomic mass of silicon is 28.09. So I'm saying the atomic mass of silicon is 28.09. Tell me the abundance and the mass of isotope silicon 30. All right. So I'm going to give people a couple minutes to try this. If you get stuck, not sure, let me know. But please do see if you can figure this out. So yeah, let's get to work. Again, if you feel stuck, not sure what to do, or if you're just like staring off in space and waiting for the answer, do let me know. I do not know if you need help if you do not tell me you need help. So, and always don't be afraid to ask for help. If you knew everything, you would not be in this class. You're here to learn. So it's okay not to know something. Or if you just want to check your answer, let me know too, and I will tell you if you're right or wrong. All right. Well, one sec. How would we find the mass of silicon-30 if we're not giving any info on it? That's what we're going to look at. All right. And we are actually given quite a bit of information about silicon-30. It's just hidden in the equation. So first, natural abundance. So hopefully everybody was able to get this one. So all of the isotopes of silicon have to equal to 100%, right? If I only have 3 isotopes of silicon, therefore all the silicon in the world is made out of these 3 isotopes, so their abundance should be 100%. So the equation for abundance is 92.9 plus 4.67 plus X. X is the abundance of silicon 30. That has to equal to 100. So do some algebra right there. Solve for X. Loading, loading, loading. You're going to really make me get out my calculator phone. Okay, so that is 3.13%. Is that right? Yes, you are going to make me get out my calculator, aren't you, phone? Sorry, I usually rely on written notes for this. And then when I try to pull up those notes, my phone decided to not do that. So let me just redo this calculation. Yep, 3.13%. Oops. Did not want to do that. $30.095. I got 3.13 when I just did it again. 92.2 minus 4.67. Yeah, should be 3.13. Oh, for mass. Gotcha. We're going to do that right now. All right. So let's look at our atomic mass equation. We know that the weight of silicon is 28.09. That is equal to fraction of isotope 1, which is 0.922, multiplied by its weight, 27.9769, plus the abundance of isotope 2, which is 0.0467, multiplied by the weight, which is 28.9765, plus the abundance of isotope 3, which is 0.0313, multiplied by its weight, which we don't know, which we're solving for. So we have one unknown, one equation. We want to solve for X. Yes, 3.13 is the natural abundance of silicon-30. Yep. So algebra time. Solve for X. So in case it's been a long time since you've done math, basically what you do is you multiply the things in the parentheses together, right? So you do 0.922 times 27.9765, and then plus the other parentheses, plus 0.0313x. You take these two numbers, you subtract that from 28.09, and then you divide each side by 0.0313. So solving for X using algebra. And what I got when I did this is 30.39 AMU. So 27.9769 multiplied by 0.922 is 25.7947 plus 28.9765 times 0.0467 is 1.353 plus 0.0313x. All right. So with that calculation out there, is there any confusion, any questions of how I went about solving this? Any questions about the math that was done? Anything at all about this type of problem? No questions. All right. So if you don't have any questions, just as a future reminder, don't be shocked when you see this question with different numbers on the test. Like, I'm going to ask it 100%. So make sure we're ready for it. And if you're not, make sure that you do understand it before test time. Because when you see this question, you'll remember this. And I'll say, I told you it's going to be on there. And it will be on there. All right. I might ask it in a different way, but we're definitely going to use this equation on test 1. All right. Now that we know where atomic masses come from, let's talk about what is called molar mass. So in chemistry, when we do experimental chemistry, we can't work with just like 1 or 2 atoms. They're way too tiny. So we work with a bigger amount of atoms. And we call that amount that we generally work with a mole. So a mole is simply 6.022 times 10 to the 23 particles or objects. I know I have 1 there, but usually people just remember 6.022 times 10 to the 23. This is called Avogadro's number. So students often get confused on when to use Avogadro's number or what Avogadro's number is. I want you to think of Avogadro's number similar to how people think of a dozen, right? If I said I want to buy a dozen eggs, how many eggs do I want? Well, that's 12 eggs, right? If I'm saying I'm working with a mole of stuff, how much stuff am I working with? 6.022 times 10 to the 23 things. So it's just a way to talk about a large amount of things in just one word. So a mole, whenever you hear a mole or Avogadro's number, just know that is a way to describe a large amount of things. Those of you who like to who have friends that have taken chemistry or follow like science things on Facebook or Instagram, you might see on October 23, people call that Mole Day, and a bunch of chemists like celebrate things and have pictures of moles. That comes from this, Avogadro's number. And on the periodic table, I already mentioned this, but the number we just calculated is actually the mass in grams of 1 mole of atoms. So silicon, the weight of 1 silicon atom is 28.09 atomic mass units, or the weight of 1 mole of silicon is 28.09 grams. And we say molar mass, which is shown here, the molar mass of silicon is 28.09 grams per mole. And we've already talked about units that have this fraction in there. What this says in English is that they're 28.09 grams for every 1 mole of silicon. That's what molar mass is. So you don't need to know the 14 after 6.022 just up to 22. You don't need to memorize that number at all. I'm going to give it to you. It's a constant. I just erased the 1,4 because I'm not going to give you the 1,4. Usually people only go to 6.022. Yeah, in this class, you'll never have to memorize constants. I will give those to you. All right, so we need to be able to use the concept of the mole and our periodic table. So right now, I want everybody, if you don't have one up yet, please get a periodic table. And I'm going to pull one up right now as well, because I do not have one up, at least a good one up. Okay, so I want to know how many sulfur atoms are there in 5.22 moles of sulfur? Okay, so we're going to start doing unit conversion using chemistry. So when doing this, I want people to keep this in mind. To go from the atom to number of moles, so number of atoms to number of moles, you have to use Avogadro's number to do that, which is 6.022 times 10 to the 23. If you want to go from numbers of moles to weights in gram, that is where molar mass comes in. And that is the periodic table. Okay, so I want to know if I have 5.22 moles of sulfur, how many atoms of sulfur is that? So I'll do A for us. And yeah, I'll do A and see if you can figure out, and I'll do A and B. How about that? And then I'll let you try to do C and D. So A, I have 5.52 moles of sulfur. And I want to know how many atoms are that. So that is Avogadro's number. Avogadro's number says for every 1 mole of sulfur, I have 6.022 times 10 to the 23 atoms. So I'm using the train track here. I have a mole at the top, mole at the bottom. Moles cancel out. And I just multiply across. And I get 3.32 times 10 to the 23, 10 to the 24, sorry, 10 to the 24 atoms. So that's how we can convert from moles to atoms using Avogadro's number. What if I want to convert between moles and weight, as in B? So B, I have 3.55 grams of zinc. I want to know how many moles it is. So if I want to convert, if we go back on the bottom here, if you want to convert between a weight and moles, you need molar mass. Molar mass is found on the periodic table. So you go to zinc on the periodic table and you find the number underneath zinc, which is 65.38. And this 65.38, the unit that we want to work with is grams per mole. That's what the unit is. Now, this always confuses people about what I'm about to do next. So I want to convert, so I'm not even going to do numbers to begin with. I'm just going to do symbols. So I want to convert from grams to moles. So who can tell me on the train track method, if I want to convert from grams to moles, do I put grams at the top or do I put grams on the bottom of my train track? You put grams on the bottom, correct. Okay, if I want to convert to moles, that means moles have to go at the top, right? Now, I go back to my number and I see it's 65.38 grams for every 1 mole. So my 65.38 must go on the bottom. My 1 goes at the top. Now my calculation is 3.55 times 1 divided by 65.38, grams cancel out, the number of moles in this amount of zinc is 0.0543 moles of zinc. So using those train track methods, we can do any conversion in the world as long as we understand how that works and we watch our units. So for the rest of time today, I want you to see if you can do C and D. Using your periodic table, tell me if I have 0.0355 moles of Ba, what's the weight in grams? Then for D, if I have 1.22 times 10 to the 27 manganese atoms, what's the weight in kilograms? So I'll give you a couple minutes to do that. If you have questions, please do let me know. Otherwise, let's get to it. And for these problems, I'll hunt around to give you more examples and put in the example folder as well. For question 1 and question 2, I'll try to put some questions, extra practice questions for you if you're still feeling a little unsure about doing these equations. And the hardest part of this might actually just be finding these elements on the periodic table once you understand the process. All right, so it's 10:50, so let's go through these somewhat quick. So Ba, we look on the periodic table. Ba has a weight of 137.328 grams per mole. So I'm starting with moles. I want to go to grams. So that's where the molar mass comes in, which is this. So I have 0.0355 mole. And I'm going from moles to grams. So moles at the bottom to cancel out to go to grams. For every 1 mole, I have 137.328 grams. Multiply everything across, and the weight of this amount of moles of Ba is 4.88 grams. D, a little more complicated, because I want my answer in kilograms. Remember from your from our metric system talk last week. And remember, I'm the keep echoing this throughout the semester. If you do not know something from the previous week, it's going to be very hard to catch up to the current week because I'm just building and building and building. So if you don't know the foundation, your castle's going to crumble. So kilograms. Remember that there are 1,000 grams in 1 kilogram. So I want to go from atoms to grams. And we look at our little flow chart on the bottom. To do that, I have to go to atoms to moles to grams. I can't go directly from atoms to grams. I have to go to moles first. Right. So to go from atoms to moles is Avogadro's number. So I have 1.22 times 10 to the 27 atoms. Avogadro's number says for every 6.022 times 10 to the 23 atoms, I have 1 mole. Atoms cancel out. I'm left in units of moles. Now in moles to go to grams, I need molar mass. So manganese, not magnesium, manganese is Mn. That is, oh, can I read my handwriting? 54.938 grams per mole. So 1 mole is 54.938 grams. Moles cancel out. My unit is grams. But I don't want grams. I want kilograms. And so for every 1,000 grams we have, that's 1 kilogram. Grams cancel out. My final unit in this equation is kilograms. So what I do is I multiply everything at the top divided by what's on the bottom. And when you do that, you should end up with 111 kilograms. It should be 3 sig figs because this is 3 sig figs. So D for right now for test 1 is probably the most complicated type of conversion we're going to do up to this point in the class, up to test 1. We'll get more convoluted as we go on, but this is, if you can do D, you're going to be good for test 1 when it comes to conversions up to this point. So I know I went over time, but is there any questions people might have about anything we talked about today? Okay, well, if not, as always, I will put a homework up. Make sure you do those. Other than that, I have nothing left for you. As always, questions, concerns, complaints, please email me. I'll be happy to address those. Otherwise, have a good rest of your Wednesday and see people Friday.